secret art that only we can see if we have the right tools to see it. So my name's John. I'm joined by Hannah, one of our co-op students at IQC. We're the Institute for Quantum Computing. We're at the University of Waterloo. And what we do there is we have a bunch of people who study mathematics, a bunch of people who study science, the physics, chemistry, as well as engineering, as well as computer scientists, people who think about what a computer is and how it works. And what we're interested in is how we can twist around some of those fields of science by thinking about the world at the very, very, very small scale. So think about a microscope. If you look through a microscope, you can see things like bacteria and cells, all these little weird things about your body. If we keep going smaller and smaller and smaller to something like 1/1000th of a meter, we start seeing that the world is made up of little things like atoms, these little tiny building blocks of the universe. This is what the world's built up on at the very basic level. And if we start being able to control the world at the very, very, very small scale, what we call the quantum mechanical scale, we can build lots of really cool things like quantum computers. And yeah, we're going to be talking a little bit about some of that at the very end. We'll just touch on it after we get to some of the light-based activities. But that's some of the research that a lot of the people, a lot of the scientists and engineers and mathematicians and computer scientists work on at places like the Institute for Quantum Computing. So today we're going to be talking about light, which is one of the things that we do have to think about a lot when we're building these kind of devices. And to get started there, I'm going to throw it over to Hannah.
Perfect. Thank you, John. I'm just going to go ahead and share my screen here. There we go. Hopefully you can all see that. So yes, today, as John said, we're going to be making secret art with polarization. And in order to do that, we actually need to be able to understand what polarization is. And to understand polarization, we first want to talk a little bit about light. So what is light? When I say light, what comes to your mind? Is there anything you've recently learned about light? What do you think of when I say light? Again, feel free to unmute yourself, put your hand up, or type it in the chat. Does anybody have any ideas? What do you think light is used for at all?
I mean, I would say light is used to be able to see what I'm doing.
Absolutely, light is for sure used to see. Any other ideas?
Anything not dark.
Anything not dark to see? Absolutely. Again, the seeing is a very important part of light there. Well, a big part of light is actually that it carries energy. So we can think about energy as heat in this case. So imagine our sun, which lights up our entire world, right? When we go outside on a sunny day, we can feel that heat on our skin, and that shows us that light has energy. Similarly, if you put your hand near a light bulb that's been on for a little while, you'll be able to feel heat off that light bulb from the light. Another example is if you put your hand near a stovetop, which again, I do not recommend doing, but if you were, you would be able to feel the heat from the stovetop, and it also glows red. So we see another correlation between light and heat there, which is energy. And even light we can't see. So for example, infrared light, which is a type we can't see with our own eyes, but we can detect it by using heat. And that's how infrared imaging works. And then we can use the idea that light carries energy to come up with a bunch of cool applications. So major one are microwaves. So microwaves is actually a form of light that we can't see with our own eyes, but they are still light and it's still transferring energy. And we use that energy to be able to heat up our food in microwaves. And we also use lasers, so high-powered lasers to be able to cut things using that energy. So now we know that light does carry energy, but how does it carry energy here? Well, light is what we call an electromagnetic wave. So I want you guys to think about light coming out of a flashlight or a laser. It travels out in a straight line. And the light is actually made up of an electric field and a magnetic field. And things like atoms and molecules can feel these fields. And the important part about this is that both the electric field and the magnetic field are perpendicular. So they're at a 90-degree angle to our direction of travel, which is represented by this black line here. Now imagine a light bulb in the center of a room. the light from that light bulb is going to spread out in the entire room, right? No matter where you are in a room, you're going to be able to see that light. So I've told you now that light is an electromagnetic wave, but how would you be able to test that light is a wave? Because I've told you, but it's not necessarily, you haven't proven it to yourself yet. Well, what we want to do is we want to take something, we want to take a quality of something we know is a wave, so we can imagine a water wave, and we want to match it to the qualities of light. So we're going to think about a water wave. So imagine dropping a pebble in the center of a lake. Think about how ripples expand and spread out from a center point where you drop that pebble, right? Can you all imagine that? Okay, and then now imagine dropping 2 pebbles in a lake, and those waves are still going to expand and spread out, but they're also going to produce something we call interference. So there's 2 types here. There's constructive interference and destructive interference. Our first kind, constructive, is when we've got one wave coming along just like this, the other wave coming along just like this, and they either meet when they're both at the top or both at the bottom. And when we look at our second image here, we can see that where our peaks are really, really clear. And then our second type, which is destructive interference, is when they meet when they're out of phase. So we've got one coming from above, maybe one coming from the bottom. And so when they meet, they actually cancel each other out. That's our destructive interference. And we can see that kind of along the fuzzy line where we don't see clear peaks or pits at all. So that's what we're going to be looking for in light. We're going to look for that wave interference. And we can actually do this through the double slit experiment. So what we're going to do is we shine a laser through a small slit. And now when a laser goes through, or when light goes through a tiny, tiny slit, it diffracts, which means it spreads out and expands from that center point, just like dropping a pebble in a body of water. So we put light through 2 slits, it expands and spreads out, and it has the chance to interfere here. And if light is in fact a wave, we should see that interference pattern, which means we should see peaks where we see constructive interference and kind of pits where we see destructive interference. So when we actually do this, these are results at the bottom. We can see constructive interference where it's really, really bright, and destructive interference where it's a little more dim there. So now we're allowed to model light as a wave, and we can use this model to predict how it's going to behave in this experiment and a bunch of other experiments as well. So let's go back to our kind of model of that single line of weight. Remember how I said that the electric field has to be perpendicular to our direction of travel? Well, there's actually a couple of different angles that this electric field can be perpendicular to our direction of travel. So imagine my arm here is our direction of travel of this light. The electric field could wave up and down just like this, or it could kind of go side to side just like this. And both ways are definitely still perpendicular. So the direction that the electric field is at is what we call the polarization of light. So I want you guys to grab your little polarizers from your kits that I believe you all have. So pull them out, and I want you to hold it up in front of your screen and twist it until you see a dark spot where it's totally dark. No light is let through at all. I'll give you guys a moment to find the spot there.
That's really cool. I thought it was just going to be like sunglasses kind of thing, but yeah, you can't see anything. That's so cool.
Yeah. So our little square is a polarizer, and our screens generally also have a polarizing filter. Now let's explain why we see this kind of dark spot appear. But first, what is a polarizer? Well, a polarizer is going to absorb any light that's waving in one direction. So we can kind of think about it like a fence or a grate. So if we've got a polarizer that's in the vertical direction, it's only going to let through light that is also in the vertical direction. And if it was in the horizontal direction, it only lets light through in the horizontal direction. So let's imagine that we have 2 polarizers and they're both in the vertical direction, let's say. The first polarizer is going to let through light in the vertical direction, and then the second polarizer is going to let through light in the vertical direction. So at the end of the day, we're still getting some light through. But if we switch our second polarizer so that it's in the horizontal direction, well, then it only lets through light that's in the horizontal direction. So our first polarizer lets through vertical light, and our second polarizer tries to let through horizontal light, but there's no horizontal light to let through, and therefore all the light gets blocked and absorbed. And that's why we see that little black square where all the light is absorbed. So what we were doing with our polarizers a second ago is our screens were polarized in one direction, and we were moving our own polarizers to match the direction where no light was let through at all. So now we know what a polarizer is, but how is that useful to us? Well, a lot of the light that we see in everyday life is unpolarized light, which isn't super useful, but some types of lights are polarized. And two big examples are road glare and reflection. So imagine you're trying to take a picture of some pretty fish in a pond. It can be kind of hard to get a clear photo because of all the reflection coming off the water. But what you can do is you can put a polarizing filter in front of your camera, and that filter is going to absorb all of our polarized light, right, our reflection, so that you're able to get a clear photo of the fish. Or imagine you're driving on a really, really sunny day. There's a lot of road glare. It's kind of hard to see. You can put on some polarized sunglasses, and it's going to absorb that glare because it's polarized. And so you're able to see a lot more clearly. Another big one is 3D movies. So how this works is the theater is actually projecting two different polarized images. And your 3D glasses that you put on make it so that one eye sees one image and the other eye sees the other polarized image. And then your brain puts that together as 3D in your head. And then finally, all your LCD screens are made up of a bunch of tiny, tiny pixels, right? Each pixel has its own polarizer that lets through a certain amount of light. So when you put all of these pixels together, you're able to create some really cool images and shapes and letters and essentially whatever you want. So that's how some LCD screens work there. There's one more thing I want to talk about before we get to our activity here, and that is birefringence. So a lot of clear plastic materials have this property called birefringence. And instead of absorbing the polarization like a lot of polarizers do, what they do is rotate the polarization. So when we put them between two cross polarizers, we're able to see how these materials rotate the polarization differently. And we can learn a lot about the structures of these materials in a really cool way. An important one here is that regular old tape is also birefringent. So we're going to actually use that idea to create some art here. So we're going to go ahead and we're going to start our activity of making polarization art. And we're going to need a couple materials. So in a second, I'm going to put our screen into a blank white PowerPoint. But we're also going to need our polarizers. You need at least 2 from your kit. And then you're going to grab a transparent surface and also some tape. Okay. And if you have the transparent surface that we provided in the lab kit, make sure to peel off the protective coating. So I'll give you guys a second to do that. And it should be on both sides there.
Yeah, I was going to say this morning, I was like, why does it look weird? It is on both sides.
Yeah.
Once you've got your, excuse me, the coating off, just let us know so we can know to go to the next step. Okay, awesome. And we'll just wait on Maria. Excuse me. Awesome. Okay, so I think we're good to go.
Okay, so our first step here is you're going to take your transparent surface and you're going to put it down and you're going to just layer on a bunch of pieces of tape in different patterns, try and get a couple pieces overlapping. Yeah, so I'll give you guys a couple minutes to do that as well.
Okay, so same thing. Once you've got your pattern on, is it just on one side, right, Hannah?
Yeah, just one side there.
Cool. Yeah, so once you've got your pattern, just let us know. Okay, we got one group done. Maria, have you got your? Perfect. Okay, Maria is good to go.
Awesome. Okay. So our next thing is we're going to hold it up to your monitor, which I'll put to a white screen in a second. And you're going to look at it through your polarizer. So I'll give everyone.
Oh my God. That's so, oh my God.
And you can also try, rotating your polarizer there and
oh my goodness,
try and take a note
cool.
about how it changes when you rotate it.
I'm going to mute myself so you don't have to hear me gasping. I'm going to add more tape.
If anybody wants to share what colors they're seeing, that could be kind of cool too, because all tapes kind of show different colors. So I'm seeing a lot of blues and a little bit of purple there. And when I rotate it, I kind of get more yellow. Blue, yeah, blue seems to be a common color.
I got some, I did a whole bunch. I've got some red. And some dark red. Blue. Yeah, I've got red. It's really cool. Marie, I think you're still on direct message. So just hit, so Maria says that she's got the same colors as you, Hannah.
Ah.
Yeah, so I've got, when I do one way, I've got, whoops, like almost like a faint reddish color. And then like purplish and then blue.
I have like one tiny square of pinkish, but that's the closest I have to red.
yeah, it's like a transparent red almost. We got some purple and yellow. Yeah, I've got some yellow too in mine. It's so cool. Like I noticed once I started overlapping a few more pieces, like it's where certain pieces overlap, so you have more in some spots or less.
Yes, exactly. Yeah.
Yeah.
It's become more vibrant with more layers.
And it changes when I rotate the square versus when I rotate the polarizer. Oh my gosh, that's so cool.
Oh, purple and yellow.
Yeah, every time I add some more tape, I'm just kind of like, what else have I got here? What else? Oh, I'm obsessed with this. So what's happening, Hannah? What am I looking at? Why are there certain
John's actually going to go into the details in a second, but do you have any guesses at all about what's happening here?
I don't. Oh,
I'm gonna actually show you guys a couple examples of people spending a lot of time on polarization art and making some really, really cool art in the end. So here's our first one. So at first, you just see it kind of all in gray and white because you're not looking at it through the polarizer. And then when you look at it through the polarizer, we can see all these colors. So I think the black on this one is just marker, but the colors we're seeing are from the tape. And then there's one more here, a little bit more intense. So yeah, this person is just using this exact same materials that we are. They have their transparent surface that's a little larger and just regular old tape. And then they just have, again, a larger polarizing filter, but the exact same materials. And they're able to make this.
I just put something in the chat every year, and everybody, if any of my staff, like coworkers were here right now, they knew how I'm reacting. I love Queen and Freddie Mercury. That's so cool. And they carved theirs instead of tape, right? Or they just carved the image to have it on there.
Yeah, they were still just using tape, and then I think they used a knife to have a more
cool,
precise. Yeah.
That's super cool.
Yeah, so those are the two examples of the polarization art I have. I'll go back to the white screen so you guys can continue to play around, see if you can make any shapes at all. Something that you can try and do, it's kind of difficult when you're holding it up to a screen, but you can try and hold the piece of tape up before you put it down and look at it through the polarizer to try and control what color you're about to see if you're, trying to make an image there. And if anybody wants to share their art with everybody, you can always take a picture of it through your polarizer and show your screen to everybody.
I'm gonna try. I'm gonna lay my laptop down so I can lay my. Oh, that's so cool that it shows up through the phone. I'm gonna take a little video so you can see when I rotate it.
Here's some of mine here. You can see without the reflection.
That's
a little bit of
really
blue, a little bit of purple.
Oh, I've got Maria's. Ooh, let's show Maria's. That's cool. I'm gonna share my screen for a sec. There's Maria's. That's really cool. You got all these little thin pieces too.
I like how you can see the one little bent piece where it gets really kind of weird there for a sec, which is kind of neat. Sometimes laying them down flat isn't the only thing you can do.
I'm gonna try and send my little video to myself so you can see it. I'll pull it up. No problem, Maria. I'm going to share my screen for a sec. There's my little video. Oh, my finger got in the way.
Oh, wow, you have some really cool patterns there.
Yeah. Do you want to share your screen again, Hannah, with that blank one?
Yeah, actually might get John to share his screen because
Yes.
he take over anyways.
Mm-hmm. Yeah, all right. I guess, yeah, we can keep working on that, but let's think a little bit. Let's go into a little bit about why we saw what we saw. So what we saw, remember what the polarizers do. If we have one polarizer, it lets through light of a certain polarization, light that's waving in one direction. If I rotate it by 90 degrees, so rotate it like that, it now lets through light that's waving in this direction instead and blocks the light that was going in the first direction. That's why if we have two polarizers in a row, we can rotate one so that it blocks out light from the other. That's what we saw with by looking at the screen and what we can see by using two polarizers in a row. But what if we have something in the middle that doesn't block polarization, but twists it around? This is what we called the birefringent material. It twisted the polarization of the light. Okay, that's what it did. But why was it then colorful? So does anyone know what color is? What does it mean for light to be a certain color? Has anyone kind of heard some things about light and color before?
I definitely have, but
yeah.
I might be interested to know if any of our guests here do. Sean, do you want to weigh in?
Like, I think it's like light is all colors at once, isn't it? And then when a color gets blocked out, that like alters what you're seeing. I think that sounds like the Magic School Bus episode I've watched before, so that's what I'm going with.
And Maria just kind of predicted what's exactly on the next slide. It's exactly like the prism and the angle. White light, what we think about as, normal light that we see around us, kind of light from the sun, light from a light bulb, is what we call white light. It actually has many different colors inside that light. So when we went to that white screen, we think about it as white, sure, because we see the color white. But it's actually being made up of many different lights. In fact, your computer screen is what we call RGB. That means it actually has red light, green light, and blue light. And to trick our eyes into thinking that it's white, it just shows you red light, blue light, and green light all at the same time. But if we do certain tricks, like the prism and the angle, we can separate that white light into its red, its green, and its blue. We can kind of see that on this example on the left here as well. Here we have 3 spotlights, one that's blue, one that's green, and one that's red. If we mix the green and the red, we get yellow. If we mix the blue and the red, we get purple. The blue and the green mixed create cyan. And if we mix all 3 together, we get this nice white light. So the tape is birefringent. It rotates the polarization of the light, but the amount that it rotates it by is different depending on the color of the light. Different colors of light will rotate by different amounts. Okay, so yeah, white light is made of many colors. Here we see, for example, this is pretty much the prism experiment, except we have a thin film that does the same thing. We have a white flashlight. We put the thin film in front of it, and we see that it's made up of, you can see some blue, you can see some red, you can see a little bit of green in the middle there. And each color of light has a different wavelength. Okay, this is a property of light. Remember, light is a wave, so each color of light actually wiggles a little bit faster than other colors. So red light has the longest wavelength. It's the lowest energy wave. Green light is somewhere in the middle. Blue light has an even faster oscillation to it, a higher frequency. And we can think about that applying to the entire rainbow of colors. So how did this work here? The white light from the screen is made of many, many colors. The tape rotates the polarization of each color just a little bit differently. And when we look through the polarizer, we only see the specific colors that were lucky enough to be rotated to the exact right angle. Now, these are just the colors that we can see. There are many colors that we can't see with our eyes, or just outside of what our eyes are capable of detecting. So you might have heard of infrared light. That's light that's just a little bit more red than red. We can't see with our eyes, but we use it in things like television remote controls. You might have heard of ultraviolet light. The sun emits a lot of ultraviolet light, which is an even higher frequency than blue and purple. And that can be used in a lot of manufacturing processes. And also, if you're worried about sunburns, is really what causes sunburns. So you have to make sure to wear the right sunscreen to make sure you're not absorbing too much ultraviolet light. Your eyes can't see it, but your skin can certainly absorb it. But it goes even beyond that as well. So that little slice right here, this is what we call the extended rainbow, or the science word for it is the electromagnetic spectrum. And it spans all these different frequencies and all these different wavelengths. So the wavelength of light is something like 100 nanometers. That's 100 billionths of a meter. So if you think about what a millimeter is about, this big or so. It is about 10,000 times smaller than that, give or take. Okay, so that's the little slice out here. That's what our eye can see, but there's all this other radiation that is light. It is an electromagnetic wave, the exact same, mathematically, the exact same physical thing as what the light our eyes can see, but used for many different purposes. So for example, we have these very, very long waves. We have waves that we use for radio and television. So these are the waves that, because they're very, very long, they spread out very, very easily. So that's what they put at the top of a radio tower so that we can hear radio all around us. By just turning on a radio, we can pick up that signal wherever we want. They're also used in technologies like magnetic resonance imaging. If you've ever either seen one of these in the hospital, it's this giant tube that you lie down and go into, and a big magnet comes on. That's why they make sure you don't have any keys on you, because or else you'll get stuck to the machine. And it basically, what it does in there is it turns on that giant magnet, shoots a bunch of radio waves at you, and uses how those radio waves interact with the atoms and molecules in your brain to make these kind of images of the inside of you. So that's a way that we use these kind of waves to actually build some imaging technologies. A little bit further in, we get kind of the signals that we use for cell phones, and we get into microwaves, which we use for things like radar, and of course, like microwave ovens, also use that exact same form of light radiation. We go a little bit further in, we get into the infrared. So infrared, like we said, is used for television remotes. It's also the exact same kind of light that we use for internet communications. If you ever heard of fiber internet being like this very, very fast internet, it's because it's using light signals, but they're outside of what we can see. They're infrared light signals. We get into our visible range, and then we go even further. We get ultraviolet, We get into X-rays that we use, of course, in X-ray imaging. And then we get up to gamma rays, which are very, very high energy. They happen in a lot of like nuclear physics experiments. And they're also often used in observatories for learning things about outer space. So all of these different beams of light, the science that we use to understand one of them is used to understand the others as well. And by doing kind of experiments like this, we can learn a lot about just what light really is. Okay. So I have one more little point to get to before we kind of break. Any questions about light before we move on? Okay, we'll come back to it though. If there will be totally time at the end if there are any remaining questions. One thing I'd like to leave you with, and this is kind of what we study at places like the IQC, is just what information is. Okay, so when you think about information, when we think about it from kind of a mathematical sense, from like a, trying to understand just what information is something that tells us something, basically. I didn't know something before, I learned some information, and that gives me new things that I now know. And we can actually think about information from a scientific perspective by thinking about the different ways that we write and provide information. So for example, I could give you information by writing it down on a note, in which case I'm actually giving you that information by writing it down, and my pen is leaving marks on the note, and that's what I'm giving to you to give you that information. Or I could tell it to you. If you're in the same room, then the information is happening because I'm sending sound waves to you, and those are providing that information. If I'm sending it to you over a Zoom call like this, then the information is being encoded in those little infrared signals that are going through the internet. All these different ways are different ways that I can package up information. Okay, we can use light as well to send that information. If you've ever seen kind of a screen like this, something, some matrix kind of thing, you might have heard about light being encoded in bits of information, these zeros and ones. This is what computers use to process information. And if I want to communicate using information, I need to find a way to send these zeros and ones over the internet, over telephone lines, anything like that. So we can use light to send these signals through optical fiber, but we need to find some way to encode this is 0 and this is 1. Yeah, we need two different signals that we can send, one corresponding to a 0 and one corresponding to a 1. And what we've been working with today is exactly a way we can do that. I can send you, say that we both have a polarizer. I send you a light beam that passes through this polarizer. That means it's definitely going this way. If you measure it, you could say, yep, it was going this way, and write down a 0. If I instead sent you a light signal that was going this way, you would measure it, find that it's blocking, and say, I guess it was going the other way. It must be a 1. So we can use polarization to send zeros and ones to each other. This is a way that we can encode information and send it at the speed of light. And there's actually some really cool experiments about this when we start thinking about how it intersects with quantum mechanics and the idea of light being made up of these particles that we call photons. There's one particular experiment going on at the Institute for Quantum Computing. It's a collaboration with the Canadian Space Agency called the Quantum Encryption in Science Satellite. It's work that they're doing with the Canadian Space Agency and partners around the world to try to get a satellite into space where they're going to be communicating to that satellite using the polarization of light, but encoded in these little tiny particles that we call photons. When they do that, they find there's a lot of really neat applications towards keeping data secure, but it all comes from how we can encode information, how we can encode zeros and ones into things like light polarization. That's all we have today. We can take it back if there are any. I hope hopefully some of you haven't kept adding tape to your thing. Maybe they've evolved a little bit in the last 10 minutes or so. But thank you so much, first off, to the museum for having us, and to you for joining us today. I hope you had a good time, and we're more than happy to answer any questions.
Yeah, excuse me. Thank you guys. That was so cool. I'm obsessed. Like, that's really, really neat. Now I kind of want to try and do like a really big detailed one. So Maria or Jenna, do either of you guys have any questions, or even Sean for Hannah or John?
I just think it's super cool as well.
Yeah.
I really like it. I wish I was artsy so I could make it cool, but I'm not.
Hey, Maria, awesome.
Thanks, Maria.
Awesome. Good to hear, Jenna. So something cool too, if you guys ever want, post, if you guys continue working on any of these, feel free to post them to the museum's Facebook or IQC. Do you guys have social media or anything people could post their pictures of what they did?
Yeah, you can find us. We're on all these different things. I think our Facebook is also at Quantum IQC. If you do find anything, feel free to post it and tag us, and we'll make sure to spread it as we can.
Yeah, I believe our Twitter is kind of has a bunch of those polarization images or that kind of art stuff already. So that was really good post as well.
Yeah, so if you play around, make sure that you you let everybody know. So yeah, I got no questions here. This was awesome. And if we've got no questions, we can end it there. So I hope everybody enjoyed themselves with this. I know I thoroughly did. Yeah, that's all I've got here today. So always check out our website of cool stuff that we've got going on at IQC. Make sure that you write down all of that to see all the cool stuff that they're doing. But we'll definitely gotta have you guys back then. So hopefully we'll be able to do this all in person. So yeah, so I'm gonna just keep Hannah, Sean, and John on after, but Maria and Jenna, thank you guys so much for joining us, and enjoy the rest of your day and have fun making secret art polarization. Awesome, thanks guys. Awesome, okay, I'm gonna end the recording.